Now we will work in general state of stress in 3D. If we consider the most general 3D state of stress at a point, then we will have 6 unknowns to determine: sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. And in this case, we'll do an analysis to find sigma n on a plane of arbitrary orientation, knowing the state of stress in plane x, y, and z. The approach is similar to what we did in case of plane stress. So the idea first is to take a certain element, and here we consider the tetrahedron element with a face perpendicular to line QN with direction, cosines, angles as sigma x, sigma y, sigma z, lambda x, lambda y, lambda z. And then we want to determine what will be sigma normal if we know the state of stress at point Q in plane X, Y, and Z. So if you look at the balance of forces on the tetrahedron element, the analysis will be very similar to the case of 2D. We should project along direction N, okay? Sum of forces along N should be 0, and this will allow us to get the value of sigma N. So in this case, we'll consider first the forces acting on different faces. You have, for example, that for this face here, you have shear forces and you have normal force. This face is parallel to plane YZ. This means that the normal force will be along X, and the normal force can be calculated as sigma X times this area. Now to calculate this area, we have the angle between the following area here, which is the area of ABC, and x-axis is equal to a certain angle alpha, in a way that cosine alpha equals to the direction cosine angle lambda x. So you know that this area here, for which x-axis is the unit vector, will be equal to delta A perpendicular to x is delta A of face ABC times cosine alpha, and cosine alpha is equal to lambda x. And therefore, we can replace delta A of this face by delta A of the triangle ABC times lambda x. This approach is similar to the one we did in 2D. If you remember, when we got the area along the two faces that are doing a certain angle with the inclined face. Similarly, we can say that the area here is equal to the area of ABC times cosine beta, where beta represents the angle between y-axis, which is the normal vector to triangle QAC, and the normal vector to triangle ABC. So then if we define the three angles of line QN with XYZ as alpha, beta, and gamma, then alpha will be equal to cosine alpha will be equal to lambda x, cosine beta will be equal to lambda y, and cosine gamma will be equal to lambda z. So now this area, to obtain this area, it's the area of triangle ABC delta A times cosine of beta, and cosine of beta is delta y. So this area is delta A sigma y. We do the similar procedure. That's the area of ABQ. We look at the angle between the normal vector to ABQ, which is along the z-axis, and the normal vector to ABC, which is along n. And then we say that the angle in between is gamma. So this area is delta A times lambda z, which is cosine gamma. Now, for each face is characterized by normal forces and shear forces. So again, going back to area BQC, which is equal to delta A times lambda x. The normal force is equal to sigma x times this area. And we have two shear forces in directions z and y. So we can find the shear forces by multiplying the shear stress tau xy by the area and the shear stress tau yz by the area. Similarly, for other faces, we can define normal force and shear forces. And then once we put all forces acting on the element, we have to say that we can project in any direction and sum of forces will be zero. We'll project on n in order to get an expression of sigma n. Because when you project on n, the shear stress along face ABC will be perpendicular to n, and then you can express sigma n function of all other stresses in x, y, and z. So here we can see the equation of projection along n. All we have to do is to project all forces along un. For example, if we start with sigma n delta A is along the normal vector un. So you can say that you have first sigma n times delta A in the positive direction. Now, let us consider, for example, this force. For this force, we have the angle between this force, which is along x-axis, and vector un. To find the projection, we know that the angle between x and un is, as we said, alpha. So we should multiply the sigma x delta A lambda x by cosine alpha. And cosine alpha is equal to lambda x. And since you have a negative projection, so you put minus. So the projection of this force on un is minus sigma x delta A lambda x, which presents the force, times cosine the angle, which is cosine alpha, which is equal to lambda x. This will give us the projection of the force normal to area BQC on un. You do similar projections for all other forces, and you say that summation of projections on un is 0. You will see that delta A is common for all terms, so you can divide all terms by delta A, and this will give you an expression of sigma n, function of the state of stress in x, y, and z, and the direction cosine angles lambda x, lambda y, and lambda z. Well, this expression is quite complex, and this is why we'll take some particular cases for simplifications. So if we can select the axis in a way that the right-hand member will reduce to the 3 terms containing only the squares of direction cosines, so if you can select x, y, z in a way that in x, y, z you have that, let's say, shear stresses are 0, which are, you know that when we have axes for which shear stress is are 0, we can say that these are the principal axes. So if you take x, y, z as principal axis, then the shear stress components will be cancelled. And you can say that if I know where are my principal axes, I can then determine sigma n, which correspond to any orientation relative to ABC, by saying that sigma n is sigma a lambda a square plus sigma b lambda b square plus sigma c lambda c square. So we can then say that coordinates axis ABC will be the principal axis of stress, and the corresponding coordinate planes are known as the principal planes of stress, and the corresponding normal stress sigma A, sigma B, and sigma C are the principal stresses at point Q. And if we know the principal stresses at point Q, we can deduce what is sigma normal for any orientation that is rotated with a certain angles alpha, beta, gamma from A, B, and C. Because once we know the unit vector of the direction of interest, we can determine sigma n as sigma a lambda a square plus sigma b lambda b square plus sigma c lambda c square. So this is to say that knowing the principal stresses, we can deduce the normal stress along any orientation of interest. Now, Mohr circle can also be used in 3D analysis of stress. What is the idea there? So if I know, let's say, the principal axis A, B, C, then I can draw on Mohr circle. So if I draw Mohr circle for this case for 3D, we know that the shear stress is 0 for principal axis. So I can represent then, if you want, 3 points, A, B, C. The 3 points will be along sigma axis because tau is 0. The first point will be characterized by sigma A 0. The second point is characterized by sigma B 0. And the third one is characterized by sigma C 0. This will give us 3 circles, because if you take the circle limited by A and B, you get the first Mohr circle. And actually, physically, it represents what? When you draw this circle, this means that you are finding state of stresses if you rotate about the axis perpendicular to plane AB. So this means if you rotate about axis C. So if you have the state of stress in plane AB, and you want to deduce the state of stress in any plane that is rotated, in any frame that is rotated at a certain angle with respect to plane, to frame AB, in plane of AB, then your rotation will be along axis C. So we can say that this circle will represent all possible state of stresses corresponding to rotation about principal axis C. And if I take circle BC, points on this circle will correspond to state of stresses obtained by rotating around axis A. Because if I know, let's say, the state of stress in this plane, and I do rotation, and I obtain a frame in plane BC, so I'm rotating around axis A, I can determine the state of stress in any area, for any angle of rotation in this plane by just looking at the Mohr circle, which is determined by a circle of diameter BC. So as we did in 2D analysis, okay? And finally, for the third circle AC, this circle corresponds to the state of stress if I do rotation about the principal axis QB. So if I rotate about B axis, then I will have a frame in plane AC. And knowing the orientation between the axis, the angle of rotation, I can use more circle to find the state of stress. So this means that in 3D analysis, I have three, if you want, circles corresponding to principal rotation about principal axis. Now, in case I have a rotation about any different axis than the principal axis, then what I will have a state of stress limited by these circles. So the state of stress will be somewhere in the shaded area, limited by the three circles corresponding to a rotation about principal axis. So this is how we can use more circle 3D analysis. Now, let us talk about the maximum shear stress. Since we have three circles, this means that for each circle, we have a certain maximum stress. For example, for circle AB, we can say that the radius of this circle corresponds to the maximum shear stress obtained if I rotate around axis QC, which is directed along C direction. Okay, so if you look again at this figure here, axis QC correspond to axis. So Q is the origin and C is the name of the axis. So line QC is the axis perpendicular to AB. So when you move along more circle AB, then you are rotating your frame about QC axis. And then the maximum possible shear you will obtain when you rotate about QC axis will be the radius of circle AB. So we have three if you want maximum shear stresses. One when you rotate around C, one when you rotate around A axis or QA axis, and one when you rotate around QB axis. Now we say that we have what we call maximum in-plane shear stress and maximum out-of-plane shear stress. This means that if I am in plane AB, I can say that the maximum shear stress obtained in plane by rotation around C, so for a frame in plane AB, is just equal to this radius. So this is this defines the maximum tau max in plane AB. But if I ask you what is the maximum shear stress without saying in plane, so you should take the maximum stress that is possible to obtain if you rotate about any axis, and then you can say here that the maximum tau max out of plane, it's not in plane AB. Here the maximum stress is in plane AC. So I can say that tau max out of plane AB, so tau max out, correspond to the radius of circle AB. So this is the maximum possible shear stress I can obtain if I do any rotation in any direction. While tau max n is the maximum shear stress obtained if I rotate about an axis perpendicular to plane formed by axis A and B. So this is the difference between maximum in-plane stress and maximum out-of-plane stress. Okay. Now, let us try to look at some specific cases. In case I have a plane stress case, this means that when we have a plane stress case, so the third principal axis will be the axis. Why? Because if I have the case of plane stress case, this means that let's say I have sigma x a value for sigma x, a value for sigma y, and sigma z is 0. Sigma z is 0, and also shear stress along z direction, tau zx and tau zy will also be 0. So in this case, we say that the third principal axis will be, of course, z-axis, because already we have two principal axes in plane xy, and the third axis will be perpendicular to plane xy and will be along z-axis. So because z-axis will correspond to the point of sigma z0 and tau equal to 0. So in this case, whenever we have a plane stress case, then in addition to the 2 points corresponding to the Mohr circle for the case of stress xy, so if I give you sigma x, sigma y, tau xy, you can draw this circle. Okay, so let's say we said that once you know sigma x, sigma y, tau xy, point big X will have as coordinate sigma x and minus tau xy, and point big Y will have as coordinates. So it will be, of course, opposite to x, because we know that the angle between x and y is 90 on the element. So on the Mohr circle, I should rotate an angle of 180 degrees from x, if I take the origin here of the circle C, the angle from Cx to Cy is 180. So once I put points x and y, the coordinates of point y are sigma y plus tau xy. Once I put point y, I can determine the diameter of my circle. The intersection with sigma axis will give me the center, characterized by coordinates sigma x plus sigma y over 2, 0. And then if I draw the circle, I will have two limiting points corresponding to sigma maximum and sigma minimum, which correspond to the principal axis AB. And then I can say that in case I have sigma A positive and sigma B negative, then the third, and I have that the third principal axis is Z, because point Z corresponds to tau, this point corresponds to sigma x and tau zx tau zy equal to 0, then I can say here that the maximum shear stress is equal to the radius of circle AB. So in this case, we say that tau max is the maximum shear stress is an in-plane shear stress, because I can obtain this maximum shear stress by rotating around the axis. So I am having a frame in plane AB having characterized by a maximum shear stress. So this is called the maximum in plane stress. So for this scenario, I have A and B, one in the positive side, one in the negative side. And then I can say that because A and B are opposite sides of the origin, the corresponding principal stresses will be the maximum and minimum normal stress for the element, and the maximum shearing stress for the element will be equal to the maximum in plane shearing stress. And to find the orientation of planes of maximum shearing stress, all I have to do is to rotate 45 degrees from the principal planes, because as you can see on Mohr circle, I'm rotating from the principal planes towards the axis of maximum shear. I'm rotating an angle of 90 degrees. So on the actual element, I am rotating an angle of 90 over 2, which is equal to 45 degrees. And if I want to illustrate this plane, I can say that, as you can see in this figure, this is knowing the principal axis. Knowing the principal axis AB, I can simply say that if I rotate an angle of 45 degrees from this axis, I can obtain the plane of maximum shear. So by doing just rotation here of plus 45 degrees, I can obtain my my plane of interest corresponding to maximum shear stress. Now, in this case, I have that sigma maximum is equal to sigma A, sigma minimum is equal to sigma B, and the maximum shear stress is half of the radius of the circle. So it's half sigma A minus sigma B. Now, another particular case is also when I have plane state stress state. So Z is the third principal axis, but now instead of having AB from opposite sides of O, A and B are from the same side of O. So as you can see here, let's say sigma A is positive and sigma B is positive. If you illustrate the 2 points, then you will have that your maximum shear stress in plane AB is not the maximum shear stress that is possible, because the third circle, the circle having the largest radius between the 3 more circles corresponding to circle AB, to circle BO, and to circle OA, the maximum radius is obtained for circle OA. So we can say that in this case, the maximum shear stress is out of plane AB. So when points A and B are on the same side of the origin, the circle defining sigma maximum, sigma minimum, and tau max for the element will not be the circle corresponding to transformation within the plane of stress. The maximum shearing stress then for the element would correspond to the radius of circle AO. This is why we say that the maximum shearing stress is half of the maximum stress, because if you look at circle AO has as diameter sigma A, which is the maximum sigma max at point A, and then the corresponding radius of this circle is sigma A over 2. So this distance would be, since this point has coordinate 0, 0, and the maximum principal stress is sigma A. So the radius of this circle will be sigma A over 2. And then the maximum shear possible in this case is equal to sigma A over 2. And it's not in plane AB, it's in plane AO. Okay, so we can say then that the plane of maximum shearing stress are obtained by rotation of 45 degrees relative to the plane of maximum normal stress. So if we illustrate this in this figure, in the following figure. So in the following figure, you have that axis, if you want, axis A, QA, okay, and axis the second plane. So the maximum, if I consider the following, this point here, so you have axis AB and you have axis Z. Here, to have the maximum stress, you will not rotate around axis Z, you will rotate around axis QB. Why? Because we said that the maximum shear stress is obtained in plane of OA, okay? Which means this plane is the one corresponding to axis QA and axis QO, which is Z axis. So now if you rotate about, let's say, if you want to go from point A to D prime, when you want to go from A to D prime, since you are rotating on Mohr circle 90 degrees, so you will rotate in the on the actual element an angle of 45, and here you are rotating on circle AO, so you are rotating about axis QB. So here axis QB, this is axis QB. Okay, so we will, let me show you here. This is axis QB. Then you should rotate perpendicular to this axis. This means that you are rotating in plane QAZ. Okay, and when you rotate an angle of 45 degrees relative to this to QA, you will get the maximum shear stress. Of course, here you have two possibilities. You can rotate in positive direction. So because if you rotate from A to D, you got the axis D prime. And if you rotate from, no, not this one here, this is D prime. So rotating in positive direction, you go to axis D prime, and rotating in negative direction, you get axis E prime. And of course, D prime and E prime are perpendicular to each other. So you can say that along these directions, along D prime and along E prime, I have the maximum shear stress. Okay, okay. Now, let us do examples on the case of 3D analysis. Let us start with the following problem. Determine the principal planes and the principal stresses for the state of plane stress resulting from the superposition of the two states of stress shown. In this figure, you have two states of stresses that are applied on an element. To be able to find, if you want, the total resulting state of stress, you should convert one of the two to the same orientation. What I mean by this, you have different orientation of stresses here in this plane, and in this figure they give you the state of stress in this plane. So what you should do, you should find, let's say for this figure, you can find what is the corresponding state of stress along these axes, along X and Y, and then you add these stresses, two stresses along XY for this state. So you get the total state of stress in plane XY. To do this, you can use, of course, the Mohr circle. Okay, so if you consider the following figure here, in the following figure, what do you know? In the following figure, you have only shear stresses. You don't have normal stresses. So this means that you are in the case of pure shear. And for a pure shear, it's very easy to draw the Mohr circle, because you have, if you take a circle, then you know the maximum shear, which is 50 megapascal. And it's corresponding to a normal stress of 0. So if you want to put your points, all you have to do is to take point Y prime with sigma average equal to 0. So this is a circle of radius 50 megapascal. This will give you the Mohr circle for this figure here, for this figure. Now, once you have the Mohr circle, you want to deduce what is the state of stress relative to axis, the horizontal and vertical axis, X and Y. To do this, to be able to find what is the state of stress in frame X and Y, all you have to know is the angle of rotation from this axis corresponding to maximum shear. So let's say we call this axis x prime, and we call this axis y prime. Now we have that tau, this is tau x prime y prime. Tau x prime y prime is positive, and we know that for point x prime the coordinates are sigma x prime, which is 0 here, minus tau x prime y prime. So point x prime is the lower point, and point y prime is the highest point here. And then to rotate from x prime to x on the element, you are rotating in counterclockwise direction in angle of 30 degrees. So on Mohr circle, you should rotate an angle of 2 times 30 degrees, which is equal to 60 degrees. And once you detect the position of x, big X, on Mohr circle, you can easily find the properties sigma x and tau xy, because you know that this point x is characterized by a coordinate along horizontal direction. This coordinate represents sigma x, and from Mohr circle, you can see that this angle here is 30 degrees, because this is 60, so this is 30. So when you project, you know that the radius of this circle is equal to 50 megapascal. So distance from O to X is 50. Projecting it on horizontal direction, you do 50 cosine 30, you get the value of sigma x. Now, the point x is characterized by coordinate sigma x, and in tau direction, it's minus tau xy. Since the coordinate of x is negative, this means that tau xy is positive, and this distance represents tau xy, which is equal to the radius of the circle, which is 50 times sine of this angle, which is 30 degrees. So tau xy is 30. Now, for coordinates of y, for point y, you know that xo and y will be collinear, because x and y constitute a diameter in the Mohr circle. Then we already found sigma x, tau xy, you still have to find sigma y. You do the projection. As you can see, sigma y is negative, and it's equal to minus sigma x, because you have, for both, the distance is r cosine 30. So sigma x equal minus sigma y, and sigma y is equal to minus 43 points. Now, once you determine the state of stress in x and y corresponding to this state of stress, now you can add it. You just have to do superposition with this case, because now you have application of, you know, the state of stress along same axis, along x and y. So now when you apply both loading on the element, the net effect in x and y will be the superposition. So you can say that, for example, to get total sigma x, I should add 43.3, which is resulting from the first load, plus the second load is applying 75 megapascal in x. So the total value of sigma x for the combined loading is 43.3 plus 75, so you get 118.3. Now same for y. So for sigma y, both pay attention if you have opposing effects. So here you have in y, you have tension, so it's plus 100, while in the first loading, it will result into compression state of stress in y, it's minus 43.3. This is why when you do the addition, you do the algebraic addition. So you do 100 minus 43.3, and you get then 56.7. Now concerning the shear stress, both shear stresses are tau xy, both are positive. So you have to add them. You have 25 megapascal plus 50 megapascal. So you get in total tau xy equal to 75 megapascal for the combined load. Now, they also asked for the principal plane and principal stresses of the superposed load. So after we determine the combined loading effect in frame xy, so we have sigma x, sigma y, and tau xy, we are able to calculate the principal stresses and the maximum shear stress. All we have to do is to say that first I have sigma average can be calculated as half sigma x plus sigma y. The radius of the resulting Mohr circle of combined load is radical sigma x minus sigma y over 2 square plus tau xy square. I can find now the value of the angle of rotation from xy, from x to the principal axis. So I can get tan of 2 theta p. Tan of 2 theta p is equal from the figure to this distance, which is 75, over the distance here, which is the difference between sigma x and sigma average. So I can find the corresponding distance, which is 30.8, and then I can get my angle theta p. Now, once I have this orientation, I can detect the orientation of principal axis with respect to my element. So if I go to my element, I can see here that I'm rotating in the counterclockwise direction in angle of 2 theta p from Cx to Ca. So if I want to represent here on this element the orientation of principal axis, I have to rotate from x-axis in angle of 2 theta p over 2. So an angle of 33.8 degrees will give me the first principal axis. And the second principal axis is oriented at an angle of, so it's perpendicular to this one. And this corresponds to an additional rotation of 90 degrees, not on the Mohr circle, of course, on the element. So on the Mohr circle, these are your principal axes. This is the first one, and this is the second one, corresponding, of course, to points on corresponding to tau equal to 0. On the element, you have this. You have the first axis obtained by rotation of an angle 2 theta p over 2, corresponding to 33.8 degrees. And now, if you rotate from x 123.8, or you rotate from here 90 degrees, you get your second principal axis. Okay, and then you can calculate the corresponding principal stresses, sigma max, sigma minima, as sigma average plus R and sigma average minus R. Another problem. For the state of stress shown, determine the maximum shearing stress when sigma y is equal to 40 megapascal and sigma y equal to 120 megapascal. Please keep in mind, when they ask you just the maximum shearing stress and they don't mention if they want the in-plane maximum shear or out of plane, this means that you can consider the maximum, the overall maximum, which can be out of plane. Okay, so when they just say maximum shearing stress, you should determine if this maximum is in plane or out of plane shearing stress. So for example, in this problem, they gave us the state of stress in plane xy, and it's, as you can see, since no sigma along z and no stress along z, this is a 2D plane stress. So if you want to plot the Mohr circle first, we have just to take 2 points. Point x characterized by coordinates sigma x minus tau xy, and point y characterized by coordinates sigma y plus tau xy, then xy will constitute the diameter of our Mohr circle. Now, we can find the center of the circle by doing sigma average equal half sigma x plus sigma y, and we can calculate the radius by using the formula of radical sigma x minus sigma y over 2 square plus tau xy square. Now, if you draw the circle, you can directly know if you are in case of maximum in plane stress or out of plane stress. As you can see, for the first case scenario when sigma y is 40 megapascal, the point of intersection with sigma axis corresponding to the principal axis are at opposite sides of O. When you have A and B at opposite sides of O, and then your principal axis, your third principal axis is Z, then you can say that the maximum, the largest radius will be of circle AB. And this means that the maximum shearing stress will be the one corresponding to the radius of circle AB. And then we can say that this is the, in this case, we have maximum in plane stress, because principal axis A and B are within plane XY, and they are obtained by rotation around the axis of a certain angle that we can determine. So 2 theta p can be calculated from Mohr circle, and we can deduce that we should rotate an angle theta p on the element to get the principal axis A and B. And these axes are in plane. They are in plane AB, and also the axis corresponding to maximum shear are also in plane AB. To get these axes, you just have to rotate 45 degrees from the principal axis. So if you rotate 45 degrees from principal axis, you get your planes, you get the direction of, if you want the axis corresponding to maximum shear stress. Now, second step is to determine the value of the maximum shear stress. So we can say that here, for the first case scenario, we have maximum in plane shear stress, and it's equal to the radius of circle AB. And then the radius of this circle is obtained is simply the radius of Mohr's circle in XY plane, which is 94.34 megapascal. So for this scenario, we have the principal stresses are sigma A equals sigma average plus radius, sigma B equals sigma average minus radius, and we have a maximum in plane shear stress obtained by doing half sigma A minus sigma B, which is equal to the radius of the circle, equals to 94.34 megapascal. Now, for the second case scenario, they told us what if sigma y now is 120 megapascal, then all the analysis will change. Because now if you draw the Mohr circle corresponding to sigma x equal 140 megapascal, sigma y equal to 120 megapascal, and tau xy equals to 80 megapascal, then you will obtain points A and B from one side of O. And this means that the maximum shear stress is out of plane AB. It is in the plane corresponding to axis Z and axis A, okay? And you can obtain the maximum shear then by rotating around axis B. So then you can say in this case, the maximum shear stress is out of plane and is equal in magnitude to the radius of this circle. And the radius of this circle is simply sigma maximum over 2. So sigma A over 2. So then you can do your calculation. You can say for the state of stress sigma x, sigma y, tau xy, sigma average is 130 megapascal. The radius of this circle is radical sigma x minus sigma y over 2 square plus tau xy square, which will give me 80.62 megapascal, then I can determine the value of sigma A and sigma B. And as you can see, both are positive. This means that the minimum stress will not be at B. The minimum stress, overall stress, will be at Z, sigma Z equal to 0. And then I can say that my maximum stress is not, if they ask for the maximum in plane stress, the maximum in plane stress will be just equal to the radius of this circle. But if they want the absolute maximum, I should take the radius of the big circle. So tau max in plane is equal to the radius of my circle, which is 80.62 megapascal. But the absolute maximum is out of plane, and the maximum shear stress, which is out of plane, is given by half of sigma A. And we calculated sigma A to be 210.6. Then tau max is 105.3 megapascal. Another problem. For the state of stress shown, determine the maximum shearing stress for these different cases. For sigma z equals 0, for sigma z equals 60 megapascal, and for sigma z equals to minus 60 megapascal. So here again, same approach. We have to put to determine the three principal axes, and the circle having the largest radius will correspond to the plane in which we have the maximum shearing stress. So to start with, as usual, I look at this figure to determine state of stress in x, y, z. What I have is sigma x is plus 170 megapascal, sigma y is plus 100 megapascal, and tau xy is plus 84 megapascal. This will allow me to put points x and y. Now, second step, I have three cases to consider. First, if sigma z is 0. If sigma z is 0, then my third axis corresponds to this point. So this is point Z. And as you can see, then the maximum shear stress corresponds to circle OA. And then I just have to say that tau max is equal to the radius of the circle, which is sigma A over 2. Now, so of course, first to be able to calculate sigma A, I need to perform the calculation of the radius. So I do sigma average. Then I do that the radius is a radical sigma average square plus half plus sigma. Sorry, the radius is a radical sigma x minus sigma y over 2 square plus tau xy square, which is 84. I get the radius. Then I say that sigma A corresponds to sigma average plus radius, and sigma B is sigma average minus radius. From my calculation, I can see that A and B are both on the same side of O. This is why if sigma z equal to 0, then the maximum radius corresponds to circle OA, and tau max is half of OA, so it's half of sigma A, so it's equal to half of 2 to 6 equal to 113 megapascal. Now, what if sigma z is plus 60 megapascal? I should locate z relative to A and B. I got that sigma A is 2 to 6 megapascal and sigma B is 44. So if sigma z is 60 megapascal, and I don't have shear stress along z because tau z x and tau zy are 0, so I can say then that the third point is somewhere in between. So it's between B and A. This is point Z then. And in this case, if Z is between B and A, so the largest circle is circle AB. This means that in this case, I have maximum in plane shear, and this maximum shear will be equal to the radius of circle AB, which is equal to the radius already calculated, which is 91 megapascal. Now, in the third scenario, they give me that sigma z is minus 60 megapascal. So if I locate z on my figure here, point z is here, let's say, so this is minus 60. So again, B is between A and Z, so the largest circle is the circle of corresponding to AZ. And then to calculate the radius of this circle, I have sigma A. Sigma A is equal to 226, and sigma Z is given to be minus 60. So the diameter of this circle is 226 plus 60. And then the radius is equal to 226 over plus 60 over 2. This means that tau max is equal to the radius, which is 286 over 2. Okay, so in the third case, the largest circle will have a radius of 143 megapascal, and therefore the maximum shear stress is out of plane and is equal out of plane xy, which is corresponding to the plane also of AB, and then tau max is out of plane and is equal to 143 megapascal, and is obtained by rotating around B axis. Okay, because when you move on more circle corresponding to AZ, then you will rotate about the third principal axis, which is B axis. Another problem, for the state of stress shown, determine the value of tau xy for which the maximum shearing stress is first 63 megapascal and second is 84 megapascal. So again, the procedure will be first to look at the figure. From the figure given, we know the state of stress in plane xy. We have that sigma x is a compressive stress, so it's minus 105 megapascal. So here just you have to put minus. Sigma y is also negative, it's a compressive stress, so sigma y is minus 42 megapascal. And for tau xy is unknown. We want to determine the value of tau xy, okay? Any way to have first the maximum shearing stress equal to 63 megapascal, and then the maximum shearing stress to be 84 megapascal. So first, here both are compressive stresses, so both are negative, but here the analysis will be similar if both are positive. So here's I considered positive cases, and just you are taking the other side of the circle. So the analysis will be similar, but to be accurate, we should put minus minus. Okay. Assume here for this solution that you have tensile stress. So sigma x will be plus 105 and sigma y will be plus 40. And the analysis will be just similar, but if you want, the circle will be from the other side, from the negative side. So if I consider the following state of stress, sigma x and sigma y given by 105 and 42, I can calculate the corresponding sigma average, which is 73.5 megapascal. And then I can say, if tau max is 63 megapascal, this means what? I want to see if this shear stress if this maximum shear stress is in plane or out of plane. So first, when you determine sigma x, sigma y, you can get sigma average. Okay, sigma average is 73.5 megapascal. So from the origin, you have a distance here equal to 73.5. Now, in the first case, you want that tau max should be 63 megapascal. Okay, and you know that because it's a 2D plane stress case, then the third principal axis will be z axis. So you know that one of your principal axis is z because you are in the case of 2D plane stress. Okay. Now, for the first scenario, in order to have tau max equals to 63 megapascal in plane xy. Okay. So here, tau max, if I plot, if you want, limits for tau max, they want that tau max should be 63. Okay. So if I plot my limits, plus 63 and minus 63, I can say then that for the first scenario, because if I take the following maximum, okay, then I should have that the maximum stress should be, I should determine if it's in plane or out of plane stress. Okay, we know that the distance between point C and point Z is equal to 73.5, okay, which is larger than the value of 63. So I can say that in this case, I should have the maximum shear out of plane, because then if I consider my 3 points, okay, I have that the maximum shear shear stress will correspond to the biggest circle, okay, and then if my biggest circle will be should pass by point Z, because I am in the case of out of plane shear stress. Then the limiting point, big A, will be anyway that circle AZ will be the circle of maximum shear stress. And in this case, I can say that sigma maximum, which should be equal to 2 times tau max, should be equal to 126 megapascal. Okay, so I have then, if I draw this circle will be the circle of a maximum shear stress, because already 63, which is the maximum, is smaller than sigma average. Okay, since my maximum is smaller than a sigma average, then I can say that my circle AB, okay, circle AB will be from the right side. So B will have a positive coordinate because sigma average is larger than because the value of sigma average, which is 73.5, is larger than the maximum radius. And the maximum possible radius of my circles correspond to 63 megapascal. Since this radius is smaller than sigma average, this means that any of my circles, okay, will have a radius that is smaller than 73.5. So my points, of course, my point B will be of coordinate, of positive coordinate, because the distance from C to B should be smaller or equal to 63. Okay, so since B is from the positive side, and already A is from the positive side because sigma A is sigma maximum, then I can be sure that both A and B are in the positive side of from the origin. And this is why in case both sigma A and sigma B are positive, then the maximum radius will correspond to circle AZ, because we have seen that when sigma B and sigma A are both positive, the maximum radius will correspond to circle AZ. And then we can say that because we know now that AZ corresponds to the maximum shear stress, which is an out of plane shear stress, then this is AZ should have the radius equal to tau max. So now once we determined tau max is 63 megapascal, which correspond to 2 times sigma A, because we have that AZ is the circle corresponding to maximum shear stress, we can locate A. Locating A will allow us to find B, because once you find A, you know that in plane AB, sigma A is the maximum, and sigma A coordinate is determined to be 2 times tau max, so 2 times 63 equals 226 megapascal. And then knowing the value of sigma average, which is 73.5, then we can determine the radius of this circle. So the radius of the circle corresponding to in plane state of stresses is equal to, this R is equal to 126 minus 73.5. So we know now the radius of the in-plane circle, which is 52.5. And we know that this radius can be calculated as sigma x minus sigma y over 2 square. And we know what is sigma x, sigma y, plus tau xy square. Tau xy is our unknown. So then we can determine the value of tau xy. So tau xy is plus or minus 42 megapascal. Okay. Now, this is the first case scenario. In the second case scenario, they gave us a value of tau max larger than 73.5. So if you take the second case, in the second case, the radius is 84. So you can say that whenever I know the radius, the maximum shear stress will correspond to the maximum possible radius. Okay. And since here the maximum possible radius is larger than 73.5, then I can say that in this case, the maximum shear stress is in plane shear stress. So because when I put the limits, 84, so since the maximum radius is 84, which is larger than the value of sigma average, okay, then I can say that whenever I consider Z, so this is point Z, okay, we have that the distance, okay, so the distance of 84 is larger than 73.5. So of course the radius will be larger than CZ, okay, and then the maximum, the value of my radius now is known. So of course I have a point B from the other side. So now I am sure that point B is from the other side of O. This means that sigma of B is negative, and sigma of A is positive. So I can then say that in this case, I have the maximum shear stress in plane AB. And therefore, all I have to do is to calculate this maximum shear stress is to find the radius of circle AB. And to do this, I say that if tau max is equal to 84 megapascal, then the center of Mohr's circle will lie at point C, and the radius will be equal to 84 megapascal. And then the value of tau xy is equal to radical of r square minus u square, which is sigma x minus sigma y over 2 square. And then I can calculate the corresponding value of tau xy. And to find the value of tau max, all I have to do is to say that tau max here will be equal to the radius of AB circle, which is 84 megapascal, and the maximum stresses, principal stresses sigma A, sigma B, are obtained by sigma average plus the radius and sigma average minus the radius. So you can see that I should do always analysis to know if the maximum shear stress is in plane and out of plane, or out of plane, and accordingly I can determine what is happening there. Another problem. For the following state of stress shown, determine two values of sigma y for which the maximum shearing stress is 80 megapascal. So again, I do same way of analysis. I look at my figure. From my figure, I determine first sigma, the state of stress given. Here, I have the case of 3D stress. It's not a 2D stress because I have stresses in all directions. I have sigma x plus 90. I have sigma z is 0, but I have that tau xz is equal to 60 megapascal. As you can see, this vector represents tau xz. Since for this face, the perpendicular is along positive x and the shear is along positive z, so I can say that tau xz equal to tau zx is equal to 60 megapascal. Now, next step will be to consider the case of to plot the Mohr circle for this state of stress. Okay, so we have for the Mohr circle in the x plane, we have that sigma average is half sigma x plus sigma z. It's 45 megapascal, and the radius is here. Please, you have a typing error. It's sigma x minus sigma z over 2 square plus tau z x square. So we get the radius of this circle. And for this circle in plane zx, we can determine the principal stresses as sigma A equals sigma average plus radius, and sigma B equals sigma average minus radius. So now to plot the circle, all we have to do here, because in general, when we take a plane, we take rotation in positive direction counterclockwise. So you can say that here I will take plane ZX, since I'm rotating from Z to X counterclockwise. This is why they will say we'll deal with the X plane. So if you want to plot the Mohr circle, you have that for point Z, the coordinates will be sigma Z minus tau ZX. And for point X, you have sigma X plus tau dx. Now, once you put these 2 points, you can draw your circle. And now, to determine the values of sigma y, they gave you the maximum shear stress. you can see that the maximum shear stress given is larger than the radius, which is 75 megapascal. The radius of your Mohr circle in XZ plane is 75 megapascal, while they want you to find the value of sigma y, the value of sigma y anyway, that the maximum shear stress would be 80. And because the maximum shear stress is 80, this means that you have the case of out of plane maximum shear. And to determine what should be sigma y to have shear stress of 80, the shear stress of 80 would correspond to a circle of radius 80. Okay. Now, what you can say that already I know 2 points A and B, which are the principal axis AB. And I know that Y is the third principal axis, because no shear tau xy tau yz is 0. So Y is the third principal axis. Now, you have two possible scenarios here. You can have the circle corresponding to the maximum radius can be or AY, and to have the maximum circle of radius 80 equal to the diameter AY, Y should be from the negative side. So B should be between A and Y. So the first possible position of Y, Y1, is this position, where AY is the circle corresponding to maximum shear. In this case, this distance is the diameter equal 2 times the radius is 160 megapascal. Since you have already calculated sigma A, which is 120 megapascal, then to have the first possibility for sigma Y is that sigma Y should be equal to minus 40 to ensure a diameter of 160. The other possibility is that the circle of maximum diameter or maximum radius is BY. So the second position of Y is the one for which A point will be between B and Y. So the second possible position of Y is from the positive side, and then BY circle will correspond to the maximum radius. And in this case, for the maximum radius BY, we have that this distance from B to Y should be 160, which is 2 times 80. And since we already determined sigma B to be minus 30, so we should have a sigma Y then to be plus 130. So the second possibility is to have sigma Y equal to plus 130. So these are the two possible scenarios that will lead to a maximum out of plane shear stress equal to 80 megapascal. And then we are done with chapter 7.